After knowing our open loop system is not adequate enough to solve our observable system, although it's not a good explanation, but let's continue. Alright, let's introduce you with the concept of the closed loop system. Alright, the closed loop system goes like this. Alright, you add in a little stuff, alright, and there will be a feedback system over here. Alright, and then alright, you go through here, alright, while you summation with your modeled system. You see, so you compare your real system with your estimated system at this point, and then once you determine the differences, then you feed back to your estimated system, alright, as a feedback with a certain constant. We call this L. Okay, if you remember, in the controller we have a feedback also, we call it K. In this case we call it L, and later on you will know that L is related to K, but we will not go into details just yet. So therefore, yeah, so this thing over here, alright, is the same thing on the presentation slide in your PDF. Okay, but just to let you take note that the labels YT is over here. Alright, you have a plus and you have a minus over here. Alright, this is Y hat T. Okay, and then you have a L over here and things like that. Okay, this arrow over here should be something like this. It's not together with your U. Yeah. Okay, which is the same thing as this already. Okay, so now we're gonna model this closed loop system. Okay, since you have understand everything, I'll just take this as our closed loop system. Now if you still remember these equations from the previous video, where I actually somewhat told you that you can model your real processes. Maybe I should write as real. This is your estimated system. Or you can model your real system, your process, with your AX plus BU over here. Okay, things like that. Alright, so we're gonna still use this one, but we're gonna add in something. Alright, what is the something that we're gonna add in? And we're gonna add in into the estimated system, because as you can see, we have a summation that feedbacks into our estimated model. Alright, so and therefore we have the estimated model with all the feedback. Then we can adjust using the feedback over here, such that the adjustment will eventually adjust to the real system. Alright, I hope that you get what I mean. Alright, so the feedback over here is to help us to model our modeled system, our estimated system, such that it adjusts it to the real system. Okay, with a certain amount of speed or whatever it is. Okay, and therefore I can just simply shift this thing a little bit over here, and then let's add in the new holy stuff. We call this LV. Alright, maybe L curly V. Alright, this L curly V, this L comes from this L, I think you know, but where is this curly V comes from? This curly V comes from the interaction for this side. Alright, this curly V is equals to your YT, because this is a plus YT, so YT minus away your Y hat T. Right, so therefore your curly V over here is equals to the difference between your output of your real system and your estimated system. Previously, in the previous videos, we actually compared the states. Now we compare the output, which is much better, right? Comparing the states is a bit tough, but if you were to compare the output, wouldn't it be better? Alright, okay, so therefore let's do up a series of derivations so that we can, in order to prove certain stuff. For this thing over here, we can just simply remove, because these are just the informations to show you certain stuff. We can name this equation 1, alright, and then we can expand this equation to more detailed stuff, okay, because we have a new friend over here. Alright, the L curly V. Okay, so this new friend over here we can simply rewrite as this thing, right? Because we have proved to you that our curly V is equals to this thing, right? It's the difference between your real system output and your estimated system output. Okay, so therefore I'll just paste this definition in the previous part. I'll just paste it over here so that you can refer it better. Alright, so I didn't cheat or filling. I simply replace my curly V as this one, which is this one. Alright, so far so good. So let's continue now. Alright, and next I can simply sub in my yt. Alright, since we know that yt is equals to cxt. Alright, your y hat t over here is equals to your cx hat t. Okay, then we can further rearrange certain stuff, and therefore let's continue, which is over here. Okay, so this thing over here comes from here, and this thing over here comes from a v. Okay, I'm simply rearranging stuff already. Okay, next we have a common term of c, as you can see, and therefore we can factorize them out, and I can call this equation 2. Alright, and this equation 2 all comes all along for what? From this system. It helps you model this system as x dot hat t. Okay, so to speak, or this one, okay, your dynamic system of an estimated model. So our estimated model can be rewritten as this thing over here. So how can we use this information? Is that we can now still compare with our processes x dot t. Alright, so we're gonna now compare this thing over here. Alright, this thing comes from your cx ax plus bu for your processes, or for your real system. Okay, so we're gonna take out its dynamic system, and we can say that this is the equation 3. Right, so now we're gonna take equation 3 minus equation 2. So we're gonna take the real system minus away the model system and see what are the differences again. Okay, so we're gonna do the same thing all along again. We have this thing over here. Alright, this thing over here is your equation 3, right, which is this one. Okay, or this one, I should say this one. While this thing over here, this thing over here is your equation 2. Okay, which is what I've shown you. Okay, and the left hand side over here, equation 3 is this one, x dot t. Alright, at the left hand side, this one is this one, minus 2. Alright, next, alright, since we know that this is the difference between the real system minus away our modeling system. Alright, so this is just the error between our real and the model system. So therefore I can somewhat cut short them. If you remember, this is the previous video. In the previous video we actually discussed this. Alright, this is your estimated state error. Alright, your state error between these two different states. Okay, or the dynamic state of your system, so to speak. Okay, and equals to, now I can evaluate all the stuff already. Alright, I'll just keep this thing over here the same. Alright, and I'm gonna elaborate these things first. Alright, what I mean is these things. Alright, so I'm gonna multiply in the minus sign. Okay, so what I will have is this thing. Alright, so far so good. The next step I'm gonna do is to also rewrite this term. Okay, this thing over here, if you still remember in the previous video, is also your estimated state error. Alright, because it is so this, because you are taking the real system of the state minus away the modeled system of the state. Alright, this state is only talking about the state at this point. Alright, the previous state, which is x dot t minus x hat dot t, if you remember, this one is for other state. Alright, other higher level state, or the first order state. This one is the 0th order state, if you so to speak. Alright, so there is a different states. This one is in terms of xt. This one is x dot t. Alright, one differentiation away. Okay, but they are all estimated state error. Okay, so I'm learning also. Alright, so I can simply rewrite this thing over here x caliber. Alright, if it's t. Alright, so if it's a differentiated one, this is x caliber dot. Alright, I hope you get what I mean. So therefore I can just simply rewrite this term. I can cut short things in a more easier way. So hold on a while. Alright, so what we can do now is that we see that but and this minus but is here, so that they can cancel each other, so therefore they cancel each other. Okay, I don't know what I'm talking but anyway, so but and minus but cancel each other. So the next step what we have is, alright, So I just cancel out the BUT. You can compare the rest lah. This thing becomes here, your minus becomes here, your minus LC becomes here. Okay, the same thing. Okay, so far so good. And the next is just that we rearrange stuff. Alright, this thing over here can be, wait hold on. So this thing over here, A can be factorized out, right? Because there are common terms. So what I have is this thing. Alright, and this thing is this thing, okay? So this thing, as you know, is also your state error or your estimated state error. Alright, so we can also rewrite this thing as your x curly bar t. Right, so what we can do is just simply to write it down. Alright, so this thing over here is being rewritten as this one. Okay, while this thing over here I just simply rewrite as this. Okay, now you have a common term, this one, right? So I can simply factorize them out again. Therefore, we have this thing all over here. Okay, so this is for your closed loop system. And as you can see, this is alright. So as you can alright, as you can see, the error over here, if we set it to be 0, this means that our state of error will be 0, right? Because when it's 0, this means that the difference between our modeled system, estimated model system, and the real processes, the difference is 0. So therefore, we have successfully modeled our system. Alright, so if we set this number equals to 0, then we can successfully model our system, right? And therefore, we have this thing over here. Correct? And then if you were to find the eigenvalues, because this thing most probably may not be 0, alright? But it somehow contradicts, alright? I don't know why, but anyway, let's continue first. So if you to find the eigenvalue for your this matrix over here, your A minus LC, alright, I have lambda I minus equals to 0, okay? So just taking the eigenvalue of this one, alright? If you were to take the eigenvalue of this one, then you can also adjust your speed. You can adjust your output. Previously, if you remember, alright, maybe I should continue in the next video to compare for the closed loop and the open loop. The takeaway from this video is that we have derived, this equation. Alright, this equation, if you set it to 0, we'll know that our real system will be equals to our modeled system. Alright, and then when you find your eigenvalues, you can know what is the output of our system already. Alright, as such, I shall see you in the next video to discuss the responses of why actually a closed loop system is way better. Alright, see you there.